Well, we're up to looking at some of the trends that we see in physical properties of the elements. There's going to be a number of new terms and vocabulary in this, and there are a number of things that you need to be able to define. So I'll point those out as we go along. Make sure as you make your notes for this topic that you're writing down clear definitions of those, because they can be things that can be asked in a exam, both in Year 11 and in your final Year 12 IB exams. And if you're thinking of moving on to HL at the end of this year, you want to make sure you have good notes and good copies of definitions and formulas that you need to know. So as we said with the periodic table, one of the reasons is it's so useful is because we see these repeating patterns or periodicity in a number of different behaviors of the elements. So some of the properties that we need to look at are things like our atomic radius, ionization energy, electronegativity, and electron affinity, which is the opposite of ionization energy. Okay, electron affinity and reactivity, both of our group 1 metals, which we need to know, and our group 17 halogens in particular are very important for us to discuss. So all of these exhibit periodicity because they're dependent on the attraction between the outer shell electrons and the nucleus. So this is dependent on two factors, okay, and we discuss these in class. So if you remember, the two factors are, of course, the distance the valence electron is from the nucleus, so distance from the nucleus. And this is defined by the shell number, okay? As the shell number or principal quantum number increases, then the distance from the nucleus increases. And as we know, if we're using two magnets, the further apart the two magnets get, the weaker the attractive force. So the attractive force that we get between these two, the further we pull them apart, the weaker it is. And we see this decaying of that attractive force in the same way with atoms, okay? So the further away the electrons are, the less tightly they're held to the nucleus. And of course, the other one is our effective nuclear charge, because that is the magnitude of the strength of attraction that the nucleus has in the first place. Okay, so something that has an effective nuclear charge of +1 is going to be holding on to its electrons far less tightly than an atom that has an effective nuclear charge of +7. So this is the first trend that we are going to talk about that you need to learn. An atomic radius, when we talk about atomic radius, we're talking about the volume of the electron cloud, really. So the nucleus is small and dense. Most of the size of an atom is defined by its electron cloud. So atomic radius decreases as we go across a period, and it increases down a group. If you think about this, this will be because as we go across a period, our effective nuclear charge increases, which means that the electrons are being pulled in more tightly to the nucleus, which is going to suck that electron cloud in more tightly around the nucleus. And that is indeed what we see as we move from lithium across to fluorine or sodium across to chlorine. This pull of the electron cloud towards the nucleus, so from +1 effective nuclear charge to +7, pulls that cloud closer around the nucleus, making the atomic radius smaller. As we move down a group, though, we're going to add a whole new shell of electrons. So we've added a shell, which means that we now expand out the size of our radius, but we still move across and get smaller. So when we look at these for comparing them, if we're looking in the same period, then we will see them get smaller based on effective charge. If we're comparing elements in the same group, then we're going to be discussing the fact that they're going to change according to the distance from the nucleus, because these are all going to have the same core charge. Then we're going to be adding a shell on with each period that we go down a group. So we will be physically increasing the size of the atom, so the atomic radii will increase. First ionization energy we have talked about a bit now. You do need to know this definition, that it is the minimum energy required to remove one electron, or the first highest energy electron, from the valence shell from 1 mole of atoms in the gaseous state. IB is big on us writing general equations, so we can see here that we can say an element of any identity X in the gaseous state can have energy put in, and we will end up with a positive ion because we have removed an electron. Okay, we've removed an electron. So we end up with a positive ion plus an electron. Okay, this is an endothermic process. It requires energy to happen. Okay, and the lower the effective nuclear charge, the less energy it's going to take to remove that, because the electrons will be held less tightly. So this is going to be dependent on the distance of the electron from the nucleus, okay, the size of the positive nuclear charge, and the shielding effect. So these two combined, of course, are our effective nuclear charge. So as we move left to right, we see an increase in ionization energy. As we move down a group, the atoms get larger, the valence electrons are held less tightly for the same effective nuclear charge, so then they become easier to remove, so the ionization energy decreases. So what this means, the greater the ionization energy of an atom, the more stable the electron configuration. Okay, so as we move across the period, we head towards the noble gases. So the more stable our electron configuration, the harder it becomes to remove an electron from that atom. And of course, the noble gases are the peak of our ionization energy, and this decreasing trend that we see here is due to the fact that we are moving down group 18. Okay, so helium, neon, argon, krypton, xenon, these are all our noble gases. Okay, and we can see we can start as we move group 1, 2 across, we see a steady increase in ionization energy as we move across a period. Electronegativity is defined as the ability for an atom to attract a bonding pair of electrons in a diatomic covalent bond. Essentially, it's the electron attracting power of an atom. Okay, we use the Pauling scale. There is a periodic table which contains the electronegativity values in your data booklet, and fluorine is our most electronegative element. So if we look at the trends here, we can see that from left to right, electronegativity increases, and it also increases up a group until we get to our most electronegative element, fluorine. Of course, group 18 doesn't have an electronegativity value. They are stable, complete octets, so they really don't have any attracting power towards electrons. They are, except for xenon, they used to be considered as inert, but highly unreactive because of that stable electron configuration. So we talked about how atomic radius decreases as we move from left to right. It is different, however, for ionic size. So ionic size, we need to consider the nature of the element. Is it a metal? Is it a non-metal? And therefore, will we be gaining electrons or losing electrons when we form an ion? Metals lose electrons to form cations, so they are always smaller than the neutral atom. Non-metals will gain electrons and form anions, so they will always be larger. Essentially what happens is when we remove the valence electrons, we've removed a shell from the cation, which means that now we have reduced the number of shielding electrons between the outermost remaining electrons and the nucleus. This increases the effective core charge for the electrons that are left, pulling the electron cloud in tight around the nucleus. In the case of forming anions, we are not increasing the number of protons, but we are increasing the number of electrons. So that causes the electron cloud to swell a bit due to the increased repulsion within that one shell, and there is no increase in the effective nuclear charge to be able to counteract that. So we see an increased size in anions from their neutral atom. Okay, so the added electrons increase the repulsion between valence electrons. So this here, the isoelectronic atoms or ions, the greater the atomic number, the smaller the radius, the greater the effective nuclear charge. Isoelectronic means atoms with the same electron configuration. Okay, so if we were to think about sodium, a sodium ion is going to be Na+. It will have 10 electrons left. It will be isoelectronic with the noble gas neon. Okay, so the noble gas neon and sodium ions would be isoelectronic. But because sodium has a greater atomic number, it would have a greater effective nuclear charge and therefore would have a smaller radius. So the physical trends that we have discussed are the atomic radius, the first ionization energy, and electronegativity. There is one that I'd like to add in here, which is electron affinity. And electron affinity is the opposite of first ionization energy. We said that the first ionization energy is the energy required to remove an electron. Electron affinity is the energy you get back when you place an electron in. Okay, so electron affinity is usually an exothermic process for things with a high core charge. This is something that we will revisit more when we do HL. We don't talk about it too much in SL other than to know electron affinity is essentially the opposite of ionization energy. It's the energy associated with putting an electron in and forming a negative ion, where ionization energy is the energy required to remove an electron. And that is it for the physical trends that we need to know from our periodic table. Just one more left to do, and that is our chemical properties.